When humanity speaks of the universe, of galaxies, stars, and cosmic mysteries, we rarely pause to acknowledge that beneath our own planet's surface lies an equally vast and enigmatic realm, the deep ocean. Although the land we inhabit covers only 30% of Earth's surface, the remaining 70% is covered by oceans, most of which lie beyond the reach of sunlight, hidden behind crushing pressure and eternal darkness. Despite containing around 80% of Earth's available living space, the deep sea remains one of the least explored environments on the planet, more mysterious to us than the surface of Mars or the Moon. The deep ocean defies our instinctive assumptions about habitability. Sunlight vanishes after a few hundred meters, plunging the realm into absolute darkness. Temperatures hover near freezing unless one reaches the rare hydrothermal vents where superheated fluids erupt from beneath the Earth's crust. At depths of 4,000 meters, pressure rises to hundreds of kilograms per square centimeter, sufficient to flatten most human-made structures. Yet remarkably, life not only survives here, but prospers, evolving into forms that challenge everything we thought we understood about biology. Unlike surface ecosystems powered by photosynthesis, deep-sea ecosystems rely on chemosynthesis. Microorganisms harvest chemical energy from hydrogen sulfide, methane, and minerals released from the Earth's crust. These microbes form the foundation for an extraordinary food web. Towering giant tube worms, ghostly transparent shrimp, pale eelpouts, and furry yeti crabs thrive around hydrothermal chimneys. These species lack pigmentation, rely on symbiotic bacteria, and possess physiological adaptations that seem almost alien. Their presence forces scientists to reconsider what conditions life truly requires. The revolutionary discovery of hydrothermal vents in 1977 at the East Pacific Rise changed the course of scientific understanding. Until then, life was believed to depend on sunlight, but the discovery of thriving ecosystems deep below the ocean shattered this notion. It suggested an alternate origin story for life, one rooted not in the warmth of shallow seas, but in the chemical-rich, scorching darkness of Earth's interior. This revelation opened new doors in evolutionary biology, geochemistry, and even astrobiology. Yet even with these groundbreaking findings, human exploration of the deep ocean remained severely limited for decades because of technological constraints. Traditional tools such as sonar mapping, deep-sea trawl nets, and weighted sapling devices provided only fragmented, often destructive glimpses of the abyss. These methods could not capture ecosystems in their natural state. True deep-sea observation, detailed, non-invasive, and in real time, was not possible until the advent of advanced, remotely operated vehicles, ROVs, and high-resolution imaging systems. This new era of exploration is epitomized by Falkor II, a cutting-edge research vessel created by the Schmidt Ocean Institute. More than just a ship, Falkor II functions as a self-contained floating research platform. Its 110-meter frame houses advanced laboratories, AI-assisted data analysis networks, sophisticated mapping arrays, and two moon pools, vertical shafts at the center of the ship that allow instruments to be lowered safely into rough seas. The vessel represents a philosophical transformation in ocean science. Exploration conducted not in isolation but in collaboration with global scientific communities. At the heart of Falkor II's capabilities lies ROV Sebastian, a versatile and powerful deep-diving robot. Capable of reaching depths up to 4,500 meters, Sebastian carries 4K cameras, robotic sampling arms, chemical sensors, and high-powered lighting systems. Connected to the ship by a kilometers-long umbilical cable, the ROV streams real-time video and data directly to the control room and through satellite links to research centers around the world. Every dive becomes, in essence, a live broadcast, a shared scientific moment accessible to experts and the public alike. In this way, deep-sea exploration becomes an act of global participation. In early 2023, Falkor II embarked on one of its most ambitious missions yet, a return to the mid-Atlantic ridge, to a region where scientists had discovered a unique hydrothermal vent ecosystem in 2000. They named it the Lost City. Unlike conventional black smoker vents that release dark metal-rich plumes, the Lost City vents release carbonate minerals that form towering white structures resembling ancient temples or cathedral spires rising from the seafloor. These formations can reach tens of meters in height, their surfaces shaped by centuries of mineral deposition. The mysterious environment inspired researchers to believe that it might hold clues to Earth's earliest life forms. The new mission sought to answer several profound questions. Is the Lost City a rare anomaly, or are similar ecosystems scattered across the ocean floor? Could these vent fields form a hidden, interconnected network with its own geological and ecological systems? And could these environments reveal how life began on Earth, and perhaps how it might exist elsewhere in the universe? To pursue these answers, Falkor II conducted a multi-phase exploration. First, its multi-beam sonar system mapped suspected areas of hydrothermal activity across the sea floor. Next, autonomous underwater vehicles, AUVs, gathered intermediate resolution data and identified promising targets. Finally, Sebastian descended into the depths for close investigation. It was during one of these dives that Sebastian entered a deep-sea valley never documented before. As its camera pierced the murky water, an astonishing landscape emerged. Massive carbonate spires towering from the seabed, glowing faintly in the artificial lights, with columns of superheated fluids jetting from fissures between them. Around these vents, life thrived in astonishing abundance. Tube worms clustered in dense colonies. Yeti crabs scraped bacterial mats from rock surfaces. Transparent shrimp flickered like faint sparks in the darkness. One vent in particular reached temperatures exceeding 400 degrees Celsius, an extreme environment in which no ordinary submarine could survive. Yet Sebastian approached within centimeters, successfully collecting fluid and mineral samples. This unprecedented achievement allowed scientists to obtain real-time, unaltered data from one of the harshest habitats on Earth. Perhaps the most captivating discovery of the mission occurred when Sebastian's cameras recorded an octopus nursery, a warm crevice where numerous octopus embryos clung to the walls, developing safely near the vent's heat. This observation challenged long-held assumptions about deep-sea reproductive strategies and suggested that hydrothermal vents may function not only as refuges for adult organisms, but also as cradles for new life. These findings reinforce the theory that Earth's earliest life forms may have originated in environments similar to the Lost City. The stable temperatures, mineral-rich fluids, and chemically reactive surfaces present ideal conditions for the formation of complex organic molecules. This deep-sea origin theory aligns closely with ongoing astrobiology research, particularly concerning icy moons like Europa, Enceladus, and Titan. Scientists now consider hydrothermal vents one of the most promising environments for extraterrestrial life. Yet although Falkor II did not discover an identical second Lost City, the team identified 3 entirely new hydrothermal vent fields, each with unique structures and chemical signatures but all thriving with life. These discoveries strongly suggest that vent ecosystems may be more widespread than previously believed, forming essential habitats across the ocean floor. The implications are profound. Studying extremophiles, organisms that survive high temperature, immense pressure, acidity, and toxic conditions, could revolutionize biotechnology. Their enzymes may function under extreme stress, offering applications in medicine, industrial chemistry, and space exploration. Understanding how these organisms protect their DNA, manage energy, and maintain cellular stability could inspire breakthroughs in human technology. The Lost City, once hidden and inaccessible, is no longer lost. Thanks to modern innovations and the dedication of ocean scientists, humanity has found a way to explore this ancient, silent world. Each dive reveals new mysteries, deepening our understanding not only of Earth's history, but of the very nature of life. Ultimately, deep-sea exploration reminds us that Earth remains a largely uncharted planet. Beneath its calm surface lies a realm full of towering structures, chemical storms, and vibrant ecosystems, an alien world within our own.